Hey everyone, we are going back to standing waves on strings to introduce the idea of harmonics. This is really the basis of how all stringed instruments are able to create sound and the methods by which they do that. So we're looking at these standing waves known as harmonics. So let's jump right into it. When we have a stringed instrument, whether it's a guitar or a violin, they create standing waves when those strings vibrate. What I mean by that is here I have a guitar, a couple parts that we need to know about. This part right here, the guitar, is called the bridge, all right? And the part right up here is called the nut. Now, the labels aren't really important, but what you should know is that the string is locked in place. The string cannot vibrate right here, and it can't vibrate right here. So if I plucked this string, it would, of course, send a wave down this string. That wave would encounter this fixed end, and just like we saw before, it would reflect. And when you pluck the string, it vibrates back and forth, up and down, not just once. So multiple wave pulses are going to travel. And so when those wave pulses hit this fixed end, they reflect. They're going to invert, if you remember, and therefore they're going to interfere. What I just described is exactly what creates standing waves. So because we have these strings with fixed ends, waves that are traveling down them reflect, they therefore interfere, and you create standing waves. This is true again for all stringed instruments. You have these fixed ends, so when the strings vibrate, they create these standing waves. Okay? Now, these standing waves that are created are what we call harmonics. And there's many different types of standing waves that might show up, and therefore there are different types of harmonics. There are some limits on the types of standing waves that can be made, though, and so that's, to be honest, kind of the basis of this whole video. I do want to point out quickly that we're going to look at one standing wave at a time, one harmonic at a time. In real life, when you pluck this guitar string here, it's creating many standing waves, not just one. All right, that's what gives a guitar its sound, is these standing waves that the guitar makes. A violin creates other standing waves. But we are just going to look at one at a time just because it's easier to analyze. All right, normally you would need computers or at least more advanced calculus or mathematics to look at multiple standing waves. So here's what I have on this next slide. Okay, as long as we meet certain boundary conditions, and I've kind of already described them, that guitar, those strings were tied at the ends, where we have the nut and where we have the bridge. If the string is tied, it obviously can't vibrate. And if the string can't vibrate, those parts are always going to be nodes. Remember that term. Nodes are the part of the standing waves that seem to stay in place. Here's a node, here's a node, here's a node, here's a node. The opposite, these parts were called antinodes. So, since all stringed instruments have the strings tied down, or at least not able to move, we have this boundary condition. What's happening at the end? They're always going to be nodes. So when I think of standing waves that can be made, there's a rule. There always has to be a node at one end and the other end. So let's draw one standing wave. Let's think, what's the easiest, kind of the simplest standing wave that I could make that has a node at the two ends? It would look something like that. Sorry, I can't draw very well. This is kind of the most basic, kind of the most boring looking standing wave. I have that dotted line to again show, remember, these waves or these strings are going up and down, up and down, up and down. This is pretty boring. It's just one hill, one crest that's undulating back and forth, but it meets the rule. Node here, node here. Notice I couldn't stop my drawing like at this location, because this location the string would be moving up and down. That would be an antinode. And I can't have an antinode because I must end and start with a node. So this diagram in red, this is called the first harmonic. It's the first standing wave that can be created. Because it's the first standing wave that can be created, it's given another term. The first one is called the fundamental. This is the fundamental. Okay? And these harmonics represent frequencies, the frequencies that these strings are vibrating. So you might see this called the fundamental frequency. Well, let's think about this string. If we assume that the length of the string is L, we're going to keep it nice and general so we can apply this to all different things. The length of the string is L. Okay, so from here to here is L. Remember, that therefore means the string is essentially L as well. Let's think, how many wavelengths are shown in this? There's 1/2 wavelength drawn. Remember, a wavelength is a whole hill and a whole valley, a complete crest and trough. I just have one of those. So 1/2 wavelengths are shown. So L, the length of this string, is comprised of half of a wavelength. That means lambda is equal to 2 times L if I solve for it. I know the wave speed equation, V equals F lambda. I'm going to solve this for frequency. Frequency is V divided by lambda. So I have frequency equals V over lambda. And what's lambda in this case? For the first harmonic, lambda is 2 times L. I could calculate the frequency of this standing wave if I know the speed of the wave on the string and I know the length of the string. Well, that's the simplest standing wave I can make. Let's try and draw the next possible standing wave. Remember, I have to start at a node and I have to end at a node. What's the next possible diagram? I could do this. Please excuse my poor drawing. That's the next possible. This first half, that was the fundamental. There's another node. The next possible diagram is the next possible time I hit a node. So this diagram, this standing wave, is called the second harmonic, or the second harmonic frequency. Well, let's again analyze. How many wavelengths do you see? There's one wavelength. One wavelength comprises the string, which again we'll say is length L. So one wavelength makes up L. So lambda is just L. That's easy. Well, remember, V equals F lambda. So if I solve for F, F is equal to V over lambda. For the second harmonic, it's V over L. Oh. Let's try the next one. You could probably guess that the next possible standing wave is called the third harmonic. All right, so I could even just write down, we're going to draw the third harmonic. What do you think? What's the next possible one you could draw? It looks like this. Ooh, boy, let me try and draw a better diagram. Third harmonic. Well, not great, but better. You might recognize a pattern. Remember, these are antinodes. The number of harmonics is translating to the number of antinodes. 1, 2, 3 antinodes, that's the third harmonic. Okay, and again, I'll draw my dash lines like that. How many wavelengths do you see? Here, there's 1.5 wavelengths, or that's 3 halves of a wavelength, and that is equal again to the length of string L. So in this case, lambda is equal to 2L over 3, if I solve for wavelength. Well, once again, frequency, I'm going to skip a step, is V over lambda. So that means the frequency of the third harmonic is equal to V divided by 2L over 3, or F3 is equal to 3V over 2L. So you can see for each of these, we can figure out how many wavelengths are present, and we could draw a diagram. We're not going to keep going forever and ever and ever, but you could. Here's all the different harmonics. They're just all the next possible standing waves that can be drawn. And you could write out the equations. You could do this every time. There is, however, a pattern. All right? Looking at this, there is a fundamental pattern that is being created. I always have the number of harmonic in the numerator, and I have 2L on the bottom. So this equation right here is a well-known physics equation. This is for the frequency of a harmonic for a wave on a string. The frequency of a given harmonic, which we'll call n, the number n harmonic that's being played, the nth harmonic, is n times v over 2L, where n is equal to 1, 2, 3, 4, etc. You could practice plugging in. If you plug in 1 right here, you get this equation. If you plug in 2 right here for the second harmonic, you get this equation because things cancel out, and so on and so forth. You could memorize this equation. This is the equation for the frequency of harmonics on a string. I don't necessarily think you should, but you could. Okay. Well, couple other things before I show you an example problem. The speed of a wave, remember, is constant. V equals F lambda for a given string. Which means if I have wavelength getting smaller and smaller and smaller, the frequency must be getting bigger and bigger and bigger. Let's look at the first harmonic, that fundamental. The wavelength is huge. It's not even fitting on this string. On this picture, now the wavelength is small enough to fit on the string. Here the wavelength is getting smaller still. I could fit one wavelength and a little more. The wavelength is decreasing as I go down my harmonics, as I get more and more complicated, which means the frequency is increasing. In fact, by definition, this is an important thing to know. The harmonics are multiples of the fundamental. What I mean by that, the second harmonic is, by definition, 2 times the fundamental, the first harmonic. The third harmonic is 3 times the fundamental. Whatever the 54th harmonic is, it must be 54 times the fundamental, the first harmonic. That can be helpful to recognize. Okay. My last slide is really just going over a classic math-based example problem. I have a violin, and let's say the string has a length of 0.7 meters. And let's say that the waves travel on a violin at 200 meters per second. When you have those strings really tight, the waves travel quickly. If the string makes the 4th harmonic, let's draw the standing wave and let's calculate the frequency. Okay, there's 2 ways to do this. All right, let's call the first way method 1, or the memorizing method. Memorizing. You could, if you want, for this class, memorize what the 4th harmonic looks like. You could look over this, you could make flashcards if you want. Okay, and you could be like, aha, that 4th harmonic, I remember, it looks kind of like this. Excuse my bad drawing. Oops, that's the 3rd harmonic, yikes. There we go, there's the 4th. 1, 2, 3, 4. All right, maybe you memorize that equation. F of n is n times v over 2L. So for the 4th harmonic, it's 4 times v over 2L. That's equal to 4 multiplied by 200, because that's the speed in this problem, times 2 times 0.7. You plug that into your calculator, and I get a frequency of 571 hertz. That's fine. If you use this on the test, I'll give you full points. But there's another method, because Mr. Thrasher hates memorizing, and I'm old, and I'm not very good at memorizing. I can still solve this problem just by knowing 2 things, the boundary conditions and being able to count. Here's what I mean by the first method. What I know for strings is they have to start and end with nodes. The 4th harmonic is just the 4th possible standing wave. Remember, here's the first possible, because I start and end at a node. Here's the second possible, start and end at a node. Here's the 3rd possible, start and end at a node. Here's the 4th possible. And look at that, I've just drawn, because it's the 4th possible, the 4th harmonic. I didn't have to memorize a picture, I just remember they always start and end at nodes. I hate memorizing this equation, and we're going to see later another equation that's very similar. If I can count wavelengths, I don't need this equation. This equation is not on the AP test. This equation is on the AP test. The frequency is equal to V over lambda. And if I can count wavelengths, let me pick orange. If I can count wavelengths, well, I can plug in here. How many wavelengths do I see? There's 2. 2 wavelengths make up the length of the string. So lambda is equal to L over 2. That's what I plug in. So the frequency, I'll flip back to green. Frequency is equal to V over L over 2. That's equal to 2 times V divided by L. That's equal to 2 multiplied by 200 divided by 0.7. And what do you know? You get the same answer. All right. To be honest, either one of these methods will work on the test. And to be honest, even though it's not on the equation sheet, my guess is if you're doing a math problem on the AP exam, this method would work too. But I don't need to memorize that equation. All right, if I can figure out how many waves are present, I can figure out an expression for lambda and plug it in. but these are harmonics. These are all the different standing waves that are created when you're playing stringed instruments. Thanks a lot for watching.